Yeah, hello dear students. You are warmly welcome to session 2 of Core Mathematics for Senior High School. Okay, so for this session we'll be looking at the number system. Alright, so without much ado, shall we kickstart? Okay, so before we set off, let's take a quick look at the session outline. So what do we seek to achieve by the end of this session? So by the end of this session, you should be able to distinguish between rational and irrational numbers, identify and explain the classifications of rational numbers, know the types of rational numbers with examples, understand the dynamics of operations with numbers, understand the concept of LCM and HCF, understand the factor tree, use the factor tree to determine products of prime factors, and determine LCM and HCF of numbers using the product of prime factors. Right, so this is basically what we seek to achieve by the end of this lesson. Right, alright, so all said and done, shall we set off with the number system? Alright, so basically the numbers that we use in mathematics, okay, we call it the real number system. Right, so the numbers used in maths across the world, we refer to it as the real numbers. Right, and we denote real numbers with the letter R. Right, so with the capital R. Right, so that is how real numbers is denoted. Right, and we have classifications of real numbers. Right, real numbers broadly are divided into two main categories, right, and that is the rational numbers and the irrational numbers. Right, so these are the two main classifications of real numbers. But then under the rational numbers we have three types. Right, so we have the integers, followed by whole numbers, and finally natural numbers. Right, so these are the three types of rational numbers. But then real numbers broadly are categorized into rational numbers and irrational numbers. Okay, alright, so let's take a quick look at the difference between rational numbers and irrational numbers. So what are rational numbers? So rational numbers are numbers that can be written in the form a over b, right, where a and b are integers, right, and b must not be 0. Right, so we have examples like 2 over 5, negative 1 over 4, and then positive 7. Right, so clearly all these numbers can be written in the form a over b. Right, so with 2 over 5, our a is 2 and our b is 5. With negative 1 over 4, our a can be negative 1, our b can be 4. With 7, our a can be 7 and our b can be 1, because any number standing on its own is divided by 1 or has a denominator of 1. So simply, rational numbers are numbers that have a numerator and a denominator. Right, so that is what we mean by rational numbers. Now there are also numbers with terminating or repeating decimal representation. So there are some rational numbers that can be expressed in decimal forms, or in fact all fractions or all numbers that can be written in the form of a numerator over a denominator can be expressed in terms of decimals. Right, and some of these decimals have terminating or repeating decimal representations, and those are the fractions that fall under the rational numbers category. So for instance, if I have a fraction 3 over 25, okay, why do I say this is a rational number? Because it obeys the rule that all rational numbers can be expressed in the form a over b. So 3 over 25 is a rational number, but then I can convert this 3 over 25 into a decimal number, right? And that gives me 0.12. Right, so 0.12 is a terminating decimal, right? So all numbers with terminating decimal representations like 3 over 25, which can be expressed in a decimal form as 0.12, is a rational number. Similarly, 1 over 3, when you are to punch your calculator 1 over 3 and you have to convert it into a decimal form, you are going to arrive at 0.3333. The 3 continues and goes on and on and on and on, right? So it has a repeating decimal representation, right? So such a number is also referred to as a rational number because it has a repeating decimal representation, right? So that is the general concept of rational numbers. And generally, rational numbers are denoted by the letter Q, right? So there is a capital Q, as you can see here, right? Alright, so let's look at irrational numbers. So obviously this is the opposite of rational numbers, right? So these are numbers that cannot be expressed in the form a over b, right, where a and b are integers, right? We'll be taking a quick look at integers very soon. Alright, so we have some examples here. We have the square root of 3, the square root of 5, 2 root 6, and then pi. Now we cannot express these numbers in the form of a over b. Alright, so we say these numbers are irrational numbers. Right, as opposed to the rational numbers, we can express them as a fraction, as a numerator over a denominator, where the numerator and the denominator are integers, right? But with irrational numbers, they are never so, right? So the root of all imperfect squares, if I'm to put it that way, right, are all irrational numbers. Right. Pi is also an irrational number. Alright, pi is an irrational number. Now, but please take note of this. The root of perfect squares are rational numbers. The root of perfect squares are rational numbers because the solution for the root is going to give you what? It's going to give you a whole number. Alright, so for instance, the root of 9 is going to give you 3. Root of 16 is going to give you 4. So root 9 is not an irrational number. It is a rational number because the result is going to give you 3, and 3 is a rational number. Right? Root 16 is going to give you 4, and 4 is a rational number. So root 16 is a rational number. So though here we are seeing examples of irrational numbers as root 3, root 5, 2 root 6. Now this radical sign or the root sign here does not necessarily make the number an irrational number. Alright, so here, because the number within the radical sign is a perfect square, the root of that perfect square becomes a rational number. Right, so that is for you to note the difference between root 3, root 5, 2 root 6 and the like, and then the root of perfect squares. Right, so irrational numbers are denoted by the letter capital H. So that is the general distinction between rational numbers and irrational numbers. Okay, let's proceed. Okay, so let's look at the various types of rational numbers. So basically there are 3 types of rational numbers, right? So the first one is integers. Right, so what are integers? they are simply positive and negative whole numbers. Right? Positive and negative whole numbers, including zero. So we have examples as -2, -1, 0, 1, 2. Right? So that is the simple definition for integers, all positive and negative whole numbers. So any negative number you can think of is an integer. Any positive number you can think of is also an integer, and then 0 is also an integer. Right? So integers are denoted by the letter capital Z. So whenever you see the letter capital Z in mathematical sense, it represents integers. Right? Okay, now let's move on to the next type. So we have whole numbers. So these are numbers that start from 0. Right? They start from 0. So examples 0, 1, 2, 3, etc. Right? So any number that starts from 0, right, so to infinity. So whole numbers, the set of whole numbers, if we are not given any range, they are infinite sets. Right? The set of whole numbers is an infinite set because it keeps going on and on and on and on. The same applies with integers, right? Unless you are given a range. I believe you are following. Yes. Okay, let's look at natural numbers. By the way, we don't have artificial numbers, right? So natural numbers. So these are numbers. These are positive numbers or integers which start from 1. Right? So they are also known as counting numbers. Right? So for sure, if you are counting a number of items, right? If you are counting a number of items, you don't start from 0. You start from 1, right? 2, 3, 4, 5, and then you keep going on in that fashion. Right? So that is why we call it the counting numbers, because we start counting from 1. Right? Nobody starts counting from negative. Right? So if we are carrying out a population census, the counting has to start from 1. Right? If we are counting the number of students in a school, we always start from 1. Right? So that is why we call it the counting numbers. Right? And that is also natural numbers. It is natural because that is the natural or the normal way of counting numbers. Right? So that is natural numbers. Alright, so let's proceed. Okay, let's look at the various kinds of numbers that we have. Right? So apart from the integers, the whole numbers, and the natural numbers, now we can have further divisions or further classifications of numbers in general, right, based on the special or the distinct characteristics they possess. Right? So we have the even numbers. Right? So what are even numbers? They are integers that can be divided exactly by 2. Right? They are integers that can be divided exactly by 2. So it means that when you divide these numbers by 2, they don't leave any remainder. Alright, so we have examples here as 2, 4, 6, 8, -4. Right? So when I divide 2 by 2, I get +1 with no remainder. When I divide 4 by 2, I get 2 with no remainder. 6 divided by 2 is 3 with no remainder. 8 divided by 2 is 4 with no remainder. -4 divided by 2 is -2 without a remainder. Alright, let's move on to odd numbers. So these are the opposite of even numbers, right? So they are simply integers that cannot be divided exactly by 2. Right? So they usually leave a remainder of 1 when divided by 2. Right? So we have examples here: -5, 1, 3, and then +7. Alright, so For sure, 3 divided by 2 will be 1, remainder 1. Right, 7 divided by 2 is going to be 3, remainder 1. Right, 1 divided by 2 is going to be 0, remainder 1. Right, so these are numbers that cannot be divided exactly by 2. Right, so they are not easily divisible by the number 2. Alright, so let's move on. So we have prime numbers. Now these are natural numbers which have only 2 factors. They have only 2 factors, and the 2 factors are 1 and the number itself. Right, so the 2 factors that are divisible by the number is just 1 and the number itself. Right, so we have examples here. We have 2, 3, 5, 7, 11. We can talk of 13. We can talk of 17, and the list goes on and on and on and on. Alright, so that is prime numbers for you. They have just 2 factors. So if I ask you to list the factors of 2, all that you tell me is 1 and 2. The factors of 3 is just going to be 1 and 3. Factors of 5, 1 and 5. Factors of 7, 1 and 7. Factors of 11, 1 and 11. So no other number can divide these numbers apart from the number 1 and the number itself. Right, so that is what we mean by prime numbers. And take note of this important point. 2 is the only prime number that is even. Right, so apart from the number 2, there is no other even number that is prime. Right, so 2 is the only prime number that is even. Right, so apart from 2, any other even number cannot fall under the category of prime numbers. So 4, 6, 8, 10 and all the other even numbers, they are not prime numbers. Right, and 2 is also the least prime number. 2 is the least prime number. Also note that 1 is not a prime number. 1 is not a prime number. Alright, let's move on to the last type of numbers here. So we have the composite numbers. Alright, so these are also the opposite of prime numbers. Right, so with composite numbers, they have more than 2 factors. Alright, they have more than 2 factors. So we have some examples here. We have 4, 6, 8, 9, 10. You can talk of 12, 15, and the list goes on and on and on. Alright, so here too, apart from the even number 2, all other even numbers are composite. All other even numbers are composite. Right, so that is composite numbers. So if I ask you to list the factors of 4, we have 1, 2 and 4. Factors of 6, we can have 1, 2, 3 and 6. Factors of 8, we can have 1, 2, 4 and 8. Factors of 9, we can have 1, 3 and 9. Factors of 10, we can have 1, 2, 5 and 10. Right, so clearly you would note that, or you realize that all these numbers have more than 2 factors. They have more than 2 factors, right? And that is what makes them composite numbers. I believe it is very clear and well explained. Okay, so let's move on. Okay, let's now talk about some operations with numbers. So when I talk of operations, I mean basic operations such as addition, subtraction, multiplication and division. Right, so let's look at some dynamics with the operations whenever we are dealing with numbers. Right, so how do we manipulate operations with numbers. So there are some rules that we have to observe. As long as operations of numbers are concerned, right? Okay, so let's start with addition and subtraction. Okay, so the first point here is that two adjacent negatives turn positive. What this means is that when two negatives meet, or when two negatives meet, they turn into what? They turn into a positive operation. Right? So for instance, if you have x minus negative y, right? Now because these two negatives are meeting side by side, they are going to change into the plus sign, right? So x minus negative y is equal to x plus y, right? So here to 3 minus negative 6, it is going to give you 3 plus 6. So the two negatives that are meeting here is going to metamorphose into the addition operation, right? So you are going to have 3 plus 6, which is equal to 9. So that is one key point you have to note whenever you are dealing with numbers in respect of the operations. So here we are the relationship between the negative operation and the positive operation, or two subtraction operations and the addition, is that when two negatives meet or come together, they are going to produce a positive operation, or an addition operation, right? Okay, let's move on. When addition and subtraction meet, the subtraction takes over, right? So for instance, if we have 5 plus negative 3, now because of this negative sign here, this addition sign is not going to make any difference, right? So we are going to interpret 5 plus negative 3 as 5 minus 3. So it means that the addition sign here does not affect it, right? So the subtraction sign here is going to take over, right? So 5 plus negative 3 is equal to 5 minus 3, and the result is 2. Alright, and I mean, typically negatives stand out more than positive. That is why you can write a positive number without necessarily putting the plus sign in front, right? So assuming I want to write positive 2, like you are seeing here, there was no need for me to place the plus sign in front of the 2. But then the fact that you are seeing the 2 standing alone connotes that, or it presupposes that this 2 here is a positive number. Alright, so really positives or plus do not stand out. But then you can't write a negative number without bringing a negative sign in front. So it tells you that the negative or the subtraction is more potent, or is more powerful than the addition or the plus sign. Alright, so, and in fact there is this saying that bad news sell more, or it spreads faster than good news. Alright, yeah, because negative is naturally stronger than positive. Okay, let's move on. So the addition of two negative numbers is still negative, right? So example, if I have negative 20 plus negative 5, now the result is going to be the negative of the sum of the two numbers here, I mean positively. So we are going to have negative of the sum of 20 and 5, and that is going to give me negative 25. I believe you are getting it. Yeah, so negative 20 plus negative 5, so virtually you are adding a negative number to another negative number. The result is going to be the negative of the sum of the numbers in their positive form, right? For example, assuming you were owing someone 20 cedis, you're owing someone 20 cedis, maybe a friend 20 cedis, and then you are owing, let's say, a brother 5 cedis. Now if I ask you to find the total of how much you owe, you will simply say 20 plus 5, right? But then because you are owing, it's going to be negative 25, right? So that is the rationale behind this principle. So whenever you're adding two negative numbers, it is simply going to be the sum of the numbers, the sum of the positive form of the numbers, then you attach the negative sign to it. I believe you get it, right? Okay, so let's move on. Okay, let's look at some key points to note with respect to multiplication, right? So the first point here is the multiplication of two negative numbers gives a positive product, right? The multiplication of two negative numbers results in a positive product, right? So for example, negative 2 times negative 9, the result is positive 18. The result is positive 18, right? So that is one key thing you have to note with multiplication. Now note that the same rule applies when the number of numbers multiplying are even, right? So here we said the multiplication of two negative numbers gives a positive product. Similarly, the multiplication of four negative numbers will give us a positive product, right? So this rule applies to it applies when the number of numbers multiplying are even, just as 2 is even, right? Okay, let's move on. The multiplication of three negative numbers gives a negative product, right? So for example, a negative 4 times negative 2 times negative 1 is equal to negative 8, right? Now the reason is that negative 4 times negative 2 will give us positive 8, right? The negative 4 times negative 2 give us positive 8, and positive 8 times negative 1 is going to give us negative 8, because the last rule tells us that the multiplication of a positive number and a negative number gives a negative product. So negative 5 times 4 is negative 20, right? So this explains why the multiplication of three negative numbers gives a negative product. So negative 4 times negative 2, based on this principle here, is going to give us a positive product. So negative 4 times negative 2, it is positive 8, and then positive 8 times negative 1, so a positive number times a negative number results in a negative product, as this principle states, right? So the multiplication of a positive number and a negative number gives a negative product, right? So negative 5 times 4, negative 20, right? So these are the key points to note under multiplication. Alright, let's move on. Okay, what about division? So what are some key points we have to note when we are dealing with the division of numbers? The division of numbers. So when dividing two negative numbers, the result is positive. When dividing two negative numbers, the result is positive. So example, negative 12 divided by negative 3 is equal to positive 4, right? And the reason is that the negative up here will cancel out the negative down here, so you will be left with positive 12 divided by positive 3, and the result is going to give us a positive 4. Alright, let's move on. When dividing one positive number by a negative number, the result is negative, right? So a negative 20 over positive 2 is equal to negative 10, right? Is equal to negative 10, right? So once one of the numbers dividing is negative, the result is going to be negative. I believe you get this simple principle. Alright, so you have to be keeping these principles on your fingertips, right? Have them on your fingertips, alright, so that it guides you as you journey in your core mathematics. Alright, okay, let's look at the third point. Division of 0 by any non-zero number is 0. Right, so what this means is that whenever you divide 0 by any number, the result is 0. Meaning that if 0 is the numerator and then any other number is the denominator, the result is still 0. So 0 divided by 1000 is still 0. 0 divided by -5 is still 0. 0 divided by any number is still 0. Right? So have this principle in mind. Any number that divides 0 or 0 divided by any number is 0. Okay, let's move on. When a non-zero number is divided by 0, the result is undefined. When a non-zero number is divided by 0, the result is undefined. Right? So example, 2 divided by 0 is undefined. Right? So long as 0 is the denominator, we cannot find an answer for it. So you can punch 2 over 0 on your calculator and you are going to get math error. Alright, because we can't arrive at a vivid answer or solution for 2 divided by 0. So long as 0 is the denominator, the answer in mathematical sense is undefined. Alright, okay, let's move on. Any number divided by 1 is the same number. Right? Any number divided by 1 is the same number. Right? So 5 divided by 1 is still 5. 1000 divided by 1 is 1000. Right? -5 divided by 1 is -5. Right? So any number divided by 1 is the number itself. So whenever you have a number dividing the number 1, the 1 being the denominator does not make any difference to the number. Alright, so that is that for this principle. Okay, given the division of two numbers, a over b is equal to c. Alright, so let's try to define each of these components. Right, so assuming I have a divided by c and the result gave me c. Now what does a represent, what does b represent, and what does the c represent? Right, so the a is known as the dividend. Right, so the dividend is more of the numerator. Right, the numerator up here is the dividend. Now we call the denominator the divisor. Right, so the number that is dividing the numerator is known as the divisor. Right, and then the result of dividing the dividend by the divisor is what we call the quotient. Right, the quotient. So let's look at a typical example here. So assuming I write 14 divided by 2. Now 14 divided by 2 is definitely 7. Now the 14 becomes my dividend, and then the 2 that is dividing the 14 becomes my divisor, whereas the result of 14 divided by 2, which is 7, becomes my quotient. Alright, so please take note of these three terminologies. We are going to make use of them in the other sessions, in the other topics, and your knowledge on this is going to help you understand how to go about those topics. Alright,